The microphone.
Oh, sorry. Best. Okay, test. I think it works.
Okay, so proceeding to the next talk, we're very happy to have Ludovico from Amsterdam. He will tell us about the solution of generalized quantum Stein's lemma. Off you go.
Okay. Thank you very much to the organizers, to Jean-Charles, for inviting me here. It's really a pleasure. It was a long trip, so I hope it's worth it for you. Okay, so right, I want to talk about this generalized quantum Stein's lemma and its solution. There's been a fairly recent development in quantum Shannon theory. But the first thing I want to do is I want to try to motivate this problem to you, why it's important and why its solution is kind of nice, a culmination of a long series of efforts. Okay, so in my claim that I want to motivate in this first part of the talk is that this generalized quantum Stein's lemma, or GQSL, really provides kind of the linchpin that connects together different topics in quantum information theory. So quantum hypothesis testing in particular, and the reversibility of quantum resources, so quantum resource manipulation. And it does so by connecting to all sorts of other concepts like thermodynamics and entanglement entropy. Okay. So why is this? So to explain why this result is so central, I have to start from this task, this fundamental task, which is called entanglement testing, or that's the way I call it. So let's say that you bought a device with a big red button, and every time you press it, you're told the device produces a bipartite entangled state ρ B, and you're given the description of this ρ B. Okay, it's what's provided by the company that manufactured it. But in fact, okay, so first of all, we should understand what entangled state means. It just means non-separable for me, and a separable state, we're doing mixed states, right? So separable state for me is something that is a convex combination of product states, okay, on Alice and Bob. Okay, so it's a bipartite quantum system. Okay, so what you suspect is that in fact the device is maliciously engineered or something, and what it does is it doesn't prepare the state ρ B, but in fact it prepares a separable state. Even if you press the button n times, what the device does is it produces a separable state. That's kind of dangerous because it would mean that it doesn't output the quantum correlations that maybe you need for your, I don't know, QKD protocol. And it does, in fact, it prepares a separable state that has no quantum correlation. So maybe the secret key you thought you would be sharing with Bob is no longer there. It's actually, it's been leaked out. And so that what you want to do is you want to decide whether this is the case. So you want to understand whether the device does what's promised or not. And we want to do this by minimizing the number of times we have to press the red button. Okay, it's kind of sample complexity if you want to. So the minimum number of uses. Okay, good. So after n uses, the picture is like this. So that there's Alice on one side, Bob on the other side. They have n systems each. Yes, please.
You are to distinguish exact separability, not rather than not.
Yes, you have to you remember you're given the description of ρ. So you're just to distinguish ρ tensor n from separable states, or ρ from separable states. Okay. Any separable state you don't know, of course, because they can. This is part of the way it's maliciously engineered, right? You don't know which separable state it will prepare. The adversary is not going to tell you. Okay, so after n uses, this is the situation. You have n systems on Alice's side, n systems on Bob's side, and you have a global state. There are two hypotheses. The first one is that, okay, it's just n times ρ. Good. So ρ tensor n. ρ is a bipartite density matrix, remember. Or hypothesis 2, it's just a global separable state. And I should stress that separability here means separability across the Alice versus Bob cut. Okay. So n systems on Alice's side, n systems on Bob's side. And this kind of classical correlations between these two sides. And how do we guess? Well, Alice and Bob they're going to perform a test, right? So they're going to perform a measurement on their system, and then they will guess hypothesis 1 or hypothesis 2. Okay, and important, so that there are two types of error to to be made by Ellis and Bob. The first one is type 1, when the right hypothesis was actually 1, but they guessed 2. Okay, so they guessed H2, but it was actually H1, so type 1 error. Okay, so what kind of this is what it was, right? So the true answer was 1, but you guessed 2, and the type 2 error is the other way around, right? But the important thing to understand here is that these 2 errors, they are not symmetric in our case, because the 2 hypotheses are not symmetric. So in other words, it could be, for example, the example I gave you, it could be much worse to to mistake a separable state for an entangled state, because then you think your device is secure and it's in fact not, than the other way around, right? Or in other words, false positives and false negatives, they're not equally consequential, as we all learned during the pandemic, I guess. I learned it then, at least. Okay, so the quantity of interest is this, is the minimum type 2 error probability for a fixed constraint on the type 1 error probability. So let's say that I give you, so say epsilon is 1%, and I want to have my type 1 error probability to be at most 1%. And now, how small can I make the type 2 error probability? This beta function, okay, so I wrote it for n equals 1. You see, like there is a maximum of separable states because the adversary is trying to maximize your probability of error. And there's a minimum of a possible tests. So the tests for us, they are just operators between 0 and the identity, okay? Just binary tests. And this is the constraint that the type 1 error probability is smaller than epsilon. Okay, so what we expect is that if we take n copies, this type 2 error probability will decay to 0 exponentially fast. So why do we expect that? Well, because you have n attempts, right? So it's maybe you're going to do a majority voting or something. Any protocol, you can do even entangled measurements, anything, literally anything that's possible. And this one should decay exponentially to 0. Because with n attempts, come on, you should be able to make it go exponentially to 0. Now the problem here is to find the coefficient, okay? The coefficient of this exponential decay, the optimal coefficient. So the best measurements you can make. And this is called the Stein exponent for entanglement testing. Okay, and so kind of formally, if you want to do things kind of in a very fancy way, you introduce this dH epsilon, which is called the hypothesis testing relative entropy. It's just minus log dH. Okay, nothing more than that. And then you look at the kind of you take the limit, you divide by n. So you see, like the minus log kind of extracts the Cn. Then I divide by n, I get C. And then I do the series of limits, right? First, the limit in n going to infinity, and then the limit in epsilon going to 0. Right? Because maybe you want epsilon to be, I don't know, very small, because of course also a type 1 error probability would like to be small. Okay, so this mysterious quantity, it's a Stein exponent. Okay, so it depends only on rho, and intuitively it should be a measure of entanglement of rho, because you see we are trying to distinguish rho from separable states. The more entangled it is, the further away it is from separable states, and therefore there should be a measure of entanglement, kind of with an operational meaning, right? It's not just any measure of entanglement; it means something. Okay, right. So it quantifies the ultimate performance of entanglement testing. Very pompous somehow. Okay, so I have to make a small detour and introduce for you another measure of entanglement, a very famous one, the relative entropy of entanglement. First of all, the relative entropy. What is the relative entropy? Well, it's a measure of statistical distance between quantum states. It was introduced by Umegaki in 1962, and it's since it's become kind of the parent quantity for all quantum information quantities that we all care about, like neutral information, coherent information, conditional entropy. And it's defined like this. So it's given 2 states, you do this kind of this weird combination of rho and sigma. You take the difference of the logs and you take the trace against rho. This infinite dimension, this works very well. And okay, so it's a measure of statistical distance between 2 states. In fact, it can be shown that it's always non-negative. Okay, it's even lower bounded by the kind of multiple of a squared of the trace distance between 2 states. Okay, but it's not symmetric, but it's a measure of distance. Okay, and now you can use it to quantify entanglement formally. You can say, okay, given any state rho AB, I want to compute how entangled it is by looking at the distance from the set of separable states in terms of the relative entropy. I put the separable state in the second argument and I minimize this. Okay, good. So this has been there forever. Like this was introduced by Vedral, Plenio, Ripping, and Knight in 1997. So it's been there for a very long time because it's a very natural quantity, a natural measure of entanglement. Okay, but for this talk and in general in quantum channel theory, we care about something called the asymptotic limit. okay, which is kind of the information theoretic equivalent of the thermodynamic limit. That is, we want to take n copies of the state, and again, the entanglement is between n copies of Alice and n copies of Bob, and we want to compute kind of the extensive part of this measure, right? So we take n copies, we compute the relative entropy of entanglement, we divide by n, and then we take the limit. So kind of the extensive part, so like the coefficient with which this object scales linearly in n. And this is really kind of equivalent to the thermodynamic limit somehow in Shannon theory. And this is it's again a measure of entanglement. It kind of obeys all properties that we want from a measure of entanglement. And it's even exactly additive. You take 2 copies of rho, it becomes twice. Just because we did this operation of regularization, it's called the limit in n. And it kind of makes it hard to compute. Yes, it does, but that's what you have to look at if you care about the asymptotic limit. Okay, so now we've got 2 measures of entanglement, the Stein exponent and the regularized relative entropy of entanglement. And it's actually easy to show that the regularized relative entropy of entanglement upper bounds the Stein exponent. And this really comes from it's kind of relatively easy. It comes from the statistical interpretation of the hypothesis of the relative entropy. It's in fact not that surprising. But the difficult question is whether there's equality. Right, and so this amounts to, again, asking yourself what are the ultimate limitations to entanglement testing, how to compute the Stein exponent. And of course, I wouldn't be standing here if these 2 were different. The 2 measures are actually the same quantity. This is exactly a statement of this generalized quantum Stein's lemma. If you want to compute the Stein exponent, which is really something meaningful, well, okay, you just you go ahead and you do this regularization there for the relative entropy of entanglement. But this is much easier. I mean, okay, it's still difficult because there is regularization, but we know how to compute this in several cases of interest. For example, we have conditions for additivity in general. So you see that as you see from the extensive list of references, this problem has an interesting history that I want to try to explain briefly. So the first pioneering paper, and I cannot stress enough how important this paper was, is by Brandão and Plenio. Actually, they have 3 papers, 1 Nature Physics and 2 Communications and Mathematical Physics. And then the second CMP, they have the full claim proof of this GQSL, this generalized quantum Stein's lemma. It's a very important paper. It introduced a lot of the framework that I'm going to discuss later, and it claimed the full proof. Okay, it turns out that the full proof is actually not there. So we found several people, including myself, found an issue in the proof. In 2022, then paper and 2023. So the proof is not correct. But in fact, there's a missing Lagrange multiplier that kind of kills the whole proof. Good. So after this, there was another claim solution by Yamasaki and Kuroiwa in January last year. Well, sorry, January this year, just before QAP. And now, okay, that was also incorrect due to an error in another paper. Interesting. Okay, so big drama. But now in 2024, we have 2 solutions, independent, by Hayashi and Yamasaki and by myself. Okay, so we are. Yeah, I think they are correct. I verified both, but but at least one should be correct. This I think I can claim. Okay, so like it's become like a big drama with lots of memes. I like the Dulwich quantum ones. Or this one that the linear increase in the number of proofs. That's good, but we haven't had any since August, so it's just too bad. Okay, right. So right now I hope I explained to you why this is important for quantum hypothesis testing, but what does the reversibility of quantum resources have to do with it? So that's my next topic. So first of all, entanglement distillation. What is entanglement distillation? Well, Sagar already kind of talked about this a bit. Well, it's the art of manipulating n copies of your favorite mixed state and extracting as many copies as possible of the EBIT, of the unit of entanglement, the 2-qubit maximum entangled state, or EBIT. Okay, via LOCC, this local operations and classical communication. And so we assume that basically Alice and Bob, they have all-powerful local quantum computers. They can do whatever, but they can only talk on the phone, okay, the classical phone. And the figure of merit, it looks something like this. Okay, so you are trying to apply an LOCC operation to your rho tensor n, so to your n copies of rho, and you try to produce as many copies as possible of the IBIT. And the rate with which you can do this conversion okay, so I allow you to make a small error, no problem, but the error will have to go to 0 as n goes to infinity. So the conversion must be asymptotically perfect somehow. Not just the error per copy, the total error to go to 0, okay? And the maximum rate with which you can do this for some LOCC protocols, this is called the distillable entanglement of your state row under LOCC. It's an insanely difficult quantity to calculate, very difficult. In fact, some people conjecture it's even undecidable to kind of to determine whether it's larger than a constant or 0. It can be 0 for some entangled states even. It's really kind of very difficult. It's kind of the most difficult of all entanglement measures, and probably also the most important. Too bad. And we also refer to this as the rate of transformation from rho to phi 2. Okay, so far so good. There is also an opposite task to entanglement distillation, which is entanglement dilution, right? The analogy is, of course, with kind of alcoholic beverages that you might want to distill or dilute. Okay, so and in this case, you want to dilute your perfect alcohol, your perfect entanglement to your state, to your target state rho AD. And again, you want to do this as efficiently as possible. So you want to God, yes, I always make this mistake. This is an infimum. It's a cost, right? So it's what you pay. So it should be an infimum of R. So so that you want to minimize the number of IBITs you spend per copy of rho. And it's called entanglement cost under LOCC. And so now there is this fantastic result by Bennett et al. 1996 that tells you that for all pure states, in fact, both of these measures, they are easily computable. But first of all, they are equal, and they are both equal to the entanglement entropy. Fantastic. This is wonderful news because the theory is then reversible. It means that you can go back and forth between any pure state and this EBIT without losing anything asymptotically. So only a sublinear amount of entanglement you will lose. That's fine. Okay, that's it's fantastic. In fact, if reversibility holds for this phi 2, it will hold for any pure state phi. So you can go back and forth between any two pure states, and the rate of interconversion is just the ratio of the entanglement entropies. See, and it's the more the entanglement, the larger of phi, the higher the rate, and of course the higher entanglement of psi, which is what you want to produce, the smaller the rate. And people call this a second law of entanglement. Some people call this because why? Because this. Due to reversibility, the entropy is the unique quantity that governs this interconversion. Okay, so the entanglement entropy is really kind of like the thermodynamical entropy for closed systems. It's the unique quantity that governs whether an adiabatic transformation exists or not. And in this case, it's the same, right? Well, kind of morally in spirit, it's the same. The rate is given by simply the ratio of the entropies. Fantastic. And so the fact that there is reversibility is really intimately connected with the fact that there is a unique entanglement measure, the entropy of entanglement. And so now the bad news is that this ceases to hold for mixed states. This was found by Vidal and Sirac at the beginning of the century, I guess. And so my favorite example, which is not the one Vidal and Sirac gave, is the antisymmetric state. So let's say you take two, Q-trits, and you take the normalized projector onto the antisymmetric subspace, which in the case is dimension 3. You see identity minus flip, normalized. There's the flip operator. Well, okay, for that state, which is entangled, turns out, as a distillable entanglement, approximately, well, okay, I won't say because we don't know how to compute that one. So for that state, the distillable entanglement is smaller than entanglement cost, strictly smaller. We can give actually explicit lower bounds. And if you do this in dimension D, this quantity on the left-hand side goes to 0 as D goes to infinity, and this quantity remains constant. And of course, the gap is in this direction. No? The distillable is always smaller than the cost, no free lunch. So you cannot create more entanglement by going back and forth. You can only lose it. Okay, nice. So, well, not nice because we lost reversibility, which is very good for having a unique measure of entanglement. So something, a go-to measure of entanglement that you compute when you don't know anything else. So now the Martin Plenio asked in 2005 whether it is possible to restore reversibility in some sense. Okay, what does it take to restore reversibility? So, and the idea is, well, okay, let's give Alice and Bob additional resources, because if they're not able to distill with what they have, that is all powerful local quantum computers and a classical communication line, let's give them more. Okay, and this, for example, you could think of giving them bound entangled PPT states. Well, it doesn't matter what PPT means, but it has to do with a partial transpose, right? One that Sagar also talked about. So this bound entangled states are states that cannot be distilled. Remember, like entangled states that have 0 distillable entanglement. Those states exist. You can give them to Alice and Bob for free, because they are not cannot distill entanglement from them directly, but they can use them to improve their distillation rates of other states. So in particular, for this alpha with PPT operations, they can get the two figures of merit to coincide for this antisymmetric state. Fantastic. So this fix works, and now you can rephrase kind of more generally this Plenio problem as the problem of finding a class of operations that makes the whole theory reversible. So reversibility means that the distillable entanglement is equal to the cost for every state, and this also means that you can go the product of the rates between rho and omega to rho is 1 for every pair of states. You can always go back and forth from rho to omega without losing anything. Okay, so spoiler alert, the PPT operations, they don't suffice in general. They were conjectured to suffice for a long time, also by Plenio himself in the first formulation of the problem, but Xin Wang and Runyao Duan showed that this is not the case in 2017. Okay, so you have to look elsewhere. Brandão, Martin Plenio and Fernando Brandão looked at this problem closely, and they came up with a possible framework to fix this whole problem, which is a set of so-called asymptotically non-entangling operations. Okay, so remember, we have to find a set of operations that does this manipulation for us with R as large as possible. Okay, so how to describe the operations? Well, okay, so let me go back to the analogy with alcohol distillation. Well, okay, so any distillation apparatus should not inject any additional alcohol into the system, right? If you start from a beverage with 0 alcohol, or from a state with 0 entanglement, you should not end up with a state that contains entanglement at the end. Otherwise, it's not a distillation. You're doing something else. And the set of operations that you create in this way, these are called non-entangling operations. Okay, do this operation suffice? It turns out also not. Too bad. But now we can make a small modification to this, which is called the set of asymptotically non-entangling operations, or A and E. And so with these operations, we require that if you start from a separable state, the entanglement content of the output should be small, vanishingly small, in fact, as n goes to infinity. And you measure this with a measure of entanglement called the global robustness of entanglement that I don't want to define. But let's just say this is Brandão and Plenio's actually contribution to identify this framework. You guarantee that whenever the initial state had no entanglement, the output will also have a small amount of entanglement, vanishingly small. Okay, and the main contribution of Brandão and Plenio is to compute both the distillable entanglement and the entanglement cost of the set of operations, these A and E operations. And it turns out that our two favorite entanglement measures appear in the regularized relative entropy of entanglement as the cost, and the Stein exponent as the distillable entanglement. And the first time I saw this, I was really shocked that kind of two entanglement measures pop up so naturally in this setting. But in fact, it's not so surprising maybe, because what is distillation? What is entanglement distillation? Well, entanglement distillation is something that behaves very differently if the initial state that you apply it to is entangled or not. If it's entangled, it will create pure entanglement. If it's not entangled, it will just not do anything, right? It will create a separable state. So somehow any protocol for entanglement distillation is a protocol that distinguishes entangled states from separable states very much. And in fact, that's why there's this connection between entanglement testing and entanglement distillation. And that's kind of summarized here. Nice. So now the problem of reversibility is just really whether these two quantities are the same. So again, the generalized quantum Stein's lemma. Okay, so this is the kind of the entanglement manipulation side of or the reversibility side of this GQSL. Any questions, maybe? Okay, good. So I hope I justified this scheme. Now, second part of the talk, I want to talk about some proof ideas, because these are, I think, quite interesting. Kind of, you need some ideas some new ideas to prove this. And so this is I guess the part where you can fall asleep. So see you in 20 minutes from a coffee break. Okay, so the first thing I want to discuss is the fact that, again, Brandão and Plenio, one of their major contributions, I think, conceptual contributions, is that this generalized quantum Stein's lemma, it's not a thing about entanglement. It has nothing to do with entanglement somehow. It's a general statement about what are called quantum resource theories. And entanglement theory is merely, well, one of the most important, if not the most important, perhaps, example of quantum resource theory. So what are quantum resource theories? Well, let's not care about that. Let's define them formally. Let's say you take a finite dimensional Hilbert space, and now for every n, you want to say that on n copies of the system, there is a set of states that are somehow easy to prepare in the lab, or for some reason, right? It could be an operational reason or a technological reason, or the fact that, you know, Alice and Bob are space-like separated, so they can only do LOCC. And so they can only prepare separable states. So for entanglement theory, this will be the set of separable states. But it could be any other set of states that for some reason are easy to prepare, like stabilizer states, convex hull of stabilizer states, anything that you like. Okay, not really anything that you like, because for this to represent a set of states that are easy to prepare in the lab, there should be a set of axioms that this family of sets obeys, right? It's a family, right? Because it's a set for every n. It's a hierarchy of sets. So what are the axioms? These are the Brandão-Plenio axioms. First one is that Fn is closed and convex. So why convex? Well, because if you flip a coin and prepare a free state, and then you forget the outcome of the coin, there should also be a free state. Closed because, well, topologically closed. Because if you can approximate a free state, let's also declare that a free state. And then also F1, so the first level contains a full rank state, for example, the maximally mixed state. So preparing the maximally mixed state should be free, or preparing some full rank state, maybe a git state, should be free. And then the family is closed on the partial trace. So if you prepare a free state of n plus m systems, and you just discard m of those, there should also be a free state of n systems. The family is closed on the tensor products. If you prepare, you know, a free state over n systems and a free state over m systems, and you just look at them together, there should also be a free state of n plus m systems. Why not? And the final axiom is that you can always shuffle the systems together. Okay, it's not a matter of how they are. It doesn't matter how they are ordered. Okay, if you have a free state over n systems, you shuffle the systems. That's again a free state. Okay, so these axioms are just for me, kind of, they are there because kind of all the resource theories we are interested in satisfy them. Okay, so for example, entanglement, but also this resource theory of magic. Okay, and so now conceptually, or at least technically for me, this is important because it will allow me to present a solution in the classical case, which of course made no sense for entanglement. There is no classical entanglement, but I can talk about classical resource theories. I can talk about a fixed alphabet x, and I can take Fn to be a set of free probability distributions over, you know, the n-fold Cartesian product of x. So this will be probability distributions over a set of sequences of symbols of x. And then I can say that this family satisfies the Brandão-Plenio axioms. And I can define a Stein exponent and a regularized relative entropy of resource for this family. Okay, for any fixed p, you do exactly what we did before. You know, you try to distinguish p from the set of free probability distributions, and that's a perfectly well-defined classical task. And you try to compute a Stein exponent, or you compute the regularized relative entropy of resource like this. This would be the classical relative entropy, the Kullback-Liebler divergence. I should also add that actually Charles Stein worked here at Stanford. So like his kind of pioneering contributions to the kind of defining this task, not exactly this task, but the task of hypothesis testing in classical information theory. It was done here. Particularly happy for this reason to be speaking here. Okay, so you can also formulate a generalized Stein's lemma in the classical case, which is okay. You remember that the Stein exponent was this limit of the hypothesis testing relative entropy. I also put a limit epsilon going to 0 there. Now I claim something even stronger. Actually, for every epsilon, if you take this limit, you get the regularized relative entropy. It doesn't matter. Epsilon doesn't matter, which makes total sense, right? So like, why should if I fix the type 1 error probability to be 1% or 2% or 3%, why should this influence the asymptotic coefficient of decay of the type 2 error probability? It shouldn't matter. It will affect kind of constant terms and other things, but not the asymptotic rate of decay. This cannot be affected. In fact, this is indeed the case. But proving this is precisely the point, that epsilon doesn't play a role. That's precisely the whole point. And it's surprisingly difficult. I mean, we just have to prove that this function is constant in epsilon. It's very difficult for some reason. Okay, but if you take the limit epsilon going to 0 formally, you get the Stein exponent, the Stein's lemma as I formulated it before. Okay. So now let's some proof ideas for this classical generalized Stein's lemma. The first thing is I want to reformulate this with the help of the max relative entropy. Okay, what is the max relative entropy? It's this quantity between two quantum states. Let's say you take the minimum lambda such that rho is upper bounded by 2 to the lambda sigma. And this just means that 2 to the lambda sigma minus rho is positive semi-definite. Okay, so this quantity is it's an upper bound to the relative entropy. It's very easy to show. It just comes from operator monotonicity of the log. But it's a very ill-behaved quantity because it can be very discontinuous in rho. And we don't want that. So to tame this quantity, we smooth it out. So we do a smoothed max relative entropy on the first argument, meaning, so the max relative entropy can be very large, can explode. So we try to make it smaller, to tame it down by taking a small epsilon ball of, a small ball of states around rho, an epsilon ball of states around rho, and we compute the Tmax between the new state and sigma, and we minimize over the states. Okay, so this quantity here, it's kind of like a bit ad hoc, but it turns out, so this was introduced by Nilanjana Datta, and then it was studied by Hayashi and Thomas Michel, and also Thomas Michel et al., Anuragan, Schuberta, and Jane, who showed that for some mysterious reason that, and this I agree, it's a bit a black magic. So the hypothesis testing relative entropy, which is the quantity we really care about, somehow it's related to this Emax relative entropy. But to go from one to the other, you have to swap epsilon with 1 minus epsilon. So dH epsilon is increasing in epsilon, while Dmax epsilon is decreasing in epsilon. You see, if you increase epsilon, you increase the size of the ball, so the minimization goes down. And this means that, and this is the starting point of my whole proof, is to go from this to this. And asymptotically, you can do this because we have the inequalities here explicitly. We know the exact relation. I mean, we have two-sided inequalities. And so that means that proving the Stein's lemma in this form with dH is the same thing as proving it in this form with Dmax. Why? Because why didn't you swap epsilon with 1 minus epsilon? We might ask, well, because this works for epsilon, for every epsilon. So swapping it is still works for every epsilon, right? So the interval 0, 1 goes to 0, 1. I could have put 1 minus epsilon here, doesn't matter. It will work for any epsilon. Okay, but now with this Dmax, this is much better because now we can proceed by contradiction. And another thing that the Nilanjana data showed is that, in fact, if you take the limit epsilon going to 0, you get this quantity, as I anticipated before. So if you remove this limit, this is precisely what we have to prove. But if you put the limit, it works, and it's easy to show. Very bizarre. So the only thing, so we have a function. So this function here, it's a function of epsilon. This function here, it's a function of epsilon. We know that for epsilon equal to 0, it does what it's supposed to do. It is equal to the value that's supposed to be always equal to. But now it could decrease in epsilon, but I'm claiming it doesn't decrease in epsilon. It's actually constant in epsilon. And that's the whole claim, is that I can remove this limit. It the equality doesn't change. Seems like a trivial claim, right? It seems like it should definitely be easy, but it's not that simple. Because it's only the limit that makes it not count. So this means that the converse is kind of easy. So it can only go down, right? Because if you take larger epsilon, it can only decrease. So it can only go down. It can only be smaller than the regularized relative entropy. So the only thing we have to show is that it doesn't go down. Okay? So the problem is achievability. So showing that this is larger than something than this. Okay, so let's say by contradiction that this is actually no, it's smaller. We are doomed. It's smaller. Okay, it's smaller than some lambda, which is strictly smaller than the regularized relative entropy. Okay, so what does now we have to unpack this. What does the lim-inf mean? Well, the lim-inf just means that this inequality works for infinitely many values of n. That's precisely what the lim-inf means. And now you see we have a minimum smaller than something. In fact, we have two minima. One is over Qn, but the second one is over the smoothing. This Tmax is a minimization over the smoothing. So we have two minima, and then it's smaller than lambda. Well, okay, that means that there exists a Qn and a smoothing such that the quantity is smaller than lambda. That's exactly what this means. This means that we can construct a smoothing of P tensor n and some Qn, which is a free probability distribution such that this inequality works. So this inequality means like for every sequence. And now we still have to use the axioms, right? We haven't used the axioms at all. Now I'm going to use one of the axioms. Axiom 5 that tells you that I can always symmetrize the probability distributions because symmetrization is a free operation. So this means that I can take always Pn and Qn to be perfectly permutationally symmetric without loss of generality. If they're not, I just make them. That means I shuffle the sequence at random. So I will get a new Pn that is even closer to P tensor n because P tensor n is invariant. So if you symmetrize, the trace distance is going to go down. This is approximation in trace distance. It's only going to go down. So one P tensor n is fixed, and the other one can only get closer. And Qn, if I symmetrize it, I get another free state. And this inequality also, symmetrization is a positive map, so it preserves the operator inequality. So there's an inequality between probability distributions, okay, so entry-wise inequality. So that means that now Pn of a sequence only depends on the type of the sequence. Same for Qn. Okay, what is the type of a sequence? One slide introduction, hands-on introduction to the theory of types. Very important in classical probability theory. This was invented by Shizar and Kerner. Have this wonderful book, 1981. So the type of a sequence, a sequence of n symbols taken from some alphabet x, is just its empirical probability distribution. Okay, so for every x, it's the number of times x appears in the sequence divided by n. That's all there is. And now there are two key observations for us. The first one is that by the law of large numbers, P tensor n, so the IID probability distribution P, will be concentrated around that type, around type P. So the kind of the sequences that are sampled according to these probability distributions will have an empirical probability distribution that's also close to P with high probability. Okay, observation number 2 is that, okay, the set of sequences is exponential in n, in size, but the set of types is only polynomial. And this is really the main observation behind this theory of types. There are very few types. So it's very important to make the analysis much easier. The set of sequences is like just the cardinality of x to the n, but because of this permutational symmetry that's intrinsic in the type, the definition of type, there are only polynomially many types. Okay, and that means that we can now there are the pictures, I promise. We can represent our Pn and Qn in type space instead of sequence space. That will be much more economical. So now we'll save a lot of space, and will also allow us to understand a lot more. Okay, so this is the representation. So let's say you have this, this is on the x-axis, I put the set of types, which, you can think of just a set of relative frequencies of every symbol. So now P tensor n will be some sort of probability distribution like this, right? So they will be kind of very peaked around type P, but of course it will have also some types that are close to P will be very represented. And now you remember the only thing we know about Pn is that it's epsilon close to P tensor n. We don't know anything else. So Pn could be like any random probability distribution. But the important thing is that since most of the weight of P tensor n is concentrated in this region, in fact, asymptotically, all the weight is concentrated in this region. There's only small tails. Well, if Pn wants to be a distance epsilon from that, and epsilon is not 1, it will have to have at least 1 minus epsilon weight here. Otherwise, they are orthogonal. It will need to have at least 1 minus epsilon weight over this ball of types where P tensor n has all the weight. Okay, good. So now there's the key step, which is the key technique I introduced to solve the problem. Is called blurring. I call it blurring. It's an operation that I do to a probability distribution, and it's made of 3 ingredients. See, 3 colors, 3 ingredients. So the input probability distribution will be Rn. So let's say that you can think of it like an input sequence, right? So you have a sequence of symbols. I do something to it. What do I do to it? First of all, I take this Q naught. This is our full support free probability distribution in the first set of the hierarchy. We have it by axiom 2, I guess. And I take m copies of it. So I take m symbols that are drawn in an IID way with respect to this free probability distribution. That's a free operation. And then I put the symbols close to next to the sequence that I have. Now I symmetrize. I shuffle all the symbols at random in a uniform way, and then I discard m symbols. Okay, by random permutation, discard m symbols. So the length of the sequence was like n here, then n plus m, and now it's back to n. And okay, it's important to realize that since Q naught has full support, somehow here I can add any sequence of symbols with some probability. Okay. And the other point is that this is by the axioms. This is composed only of free operations, so it maps free states to free states. Okay, right? Because this adding tensor product with a free operation is a free operation. Symmetrization is a free operation. Discarding symbols is a free operation. Okay. Okay. So what does it do? Right. So you start from we were here, right? So P tensor n, epsilon close Pn, and then Pn is upper bounded by some free probability distribution with some coefficient. Now I blur everything. So P tilde n will be the blurred probability distribution, and that's still upper bounded by this quantity because the blurring is a positive map. So you have this 2 to the lambda coefficient, and then you have this new blurred free probability distribution, which is again another free probability distribution. Okay, but in the picture, what does it do? What does blurring do, right? So we are applying it to this Pn, not to this P tensor n, to Pn. What does it do? Well, it's called blurring because it adds some noise, right? Well, what we're doing is we're adding some noise. We're adding some symbols with some probability. And what this means is that it kind of effectively blurs the probability distribution, so it blurs the peaks. It does something like this. Some of the weight of the peaks is redistributed to close by types because you will be changing the type randomly because you're adding symbols of every sort, essentially. Of every species, you're adding some symbols. And this will mean that your type will shift. You know, the empirical frequency will shift. So and what happens is that really the peaks get redistributed to nearby types. And you can control this quantitatively very easily because it's classical, so everything's easy. Somehow you can control all the frequencies. It's relatively straightforward. And in particular, what's interesting for us is what happens inside this type ball. What happens is that this P tilde n, so the new blurred probability distribution, now it covers, well, I wrote uniformly, but it has some non-trivial weight on all the types in the
Should you share your screen?
Please enter the meeting passcode followed by the pound sign.
Click on this. Yes.
You are in the meeting now. Recording.
Okay, good. So how much time do I have? In fact, I lost track of maybe 10 minutes. 7 minutes. Okay, good. Try to be real quick. Maybe I should also do. No, because it's I can see the. Yeah, exactly. And because it's a PDF now. Okay, yes. Like this. Fantastic, more or less. Okay. Right. So we are here. Okay. So this is kind of, it's covered uniformly, more or less. And so this means that this is kind of the key step. Now it means that, you know, up to cutting the tails of P tensor n, you get this new probability distribution P prime n that it's upper bounded by up to a small exponential factor, but a small exponential factor by this P tilde n. And at eta is very small because we just cut off the tails of P tensor n. And so now you can concatenate this with the inequality we had before on P tilde n, and you get this. So you get that P prime n is upper bounded by a free probability distribution with this exponential coefficient, which is basically lambda, n lambda. And so this, like if you go back to the smoothed max relative entropy, this is exactly what this means. And now you can take the limit. You can divide by n, take the limit, and you get precisely this. And this works for every eta. For sufficiently large n, this works for every eta because eta was just the weight of the tail. And so now we can take the limit eta going to 0, but remember I told you that this one is exactly what we want. This is the limit eta going to 0. So now that this black magic makes appear the relative entropy, regularized relative entropy on the side, and we got a contradiction. Okay, so somehow this blurring technique really relates different smoothed values of different smoothed values of this D max for different eta. So the kind of the value when epsilon is kind of large to the value when epsilon is small or eta is small. And that's why we can prove it this way. Okay, so very briefly the quantum version, because the blurring step is the same, but the quantum blurring map is exactly the same as before. So you take your system, you add free states, you symmetrize, you trace away your systems. The blurring map is exactly the same. It works, but to make it work, you need this quantum blurring lemma, which I state here in an imprecise way, which is the same statement as before. If you start from a sequence of states that's not orthogonal to an IID state, and you blur it, you will approximately dominate your IID state. So this approximate domination means that if you take your state, you subtract, you know, with a small exponential coefficient, the blurred state, and you take the trace of the positive part, so the sum of the positive eigenvalues, this goes to 0. So essentially, this operator is approximately negative definite in the limit, which means exactly that this is rho tensor n is smaller than the blurred state. Okay, so there's this asymptotic domination, but the proof of the blurring lemma is very different. Okay, so the first step is purification. I want to show you the proof, and I just want to highlight one thing. The first step is purification. So I purify everything. I purify rho, and I purify rho tensor n, and I purify rho n. So the purification of rho, let's call it 0. So it's just a pure state that extends rho, right? Kind of church of larger Hilbert space. And now the only way I found of analyzing the corresponding limit, but it's by no means the best one. It's probably not the best one, but the only way I found it is to embed this system into the Fock space, right? Because we take n going to infinity, so it makes a lot of sense that we embed it into an infinite dimensional space. And the embedding is just you know, like kind of 0 tensor n, it goes to the vacuum. So my rho tensor n effectively goes to the vacuum, and anything that's not rho tensor n will contain some excitations. And now I know how to solve the problem in the limit in this Fock space. But this is it's a very strange technique. It's very bizarre. You should be able to analyze this problem for every n without going to this infinite dimensional limit. But somehow that's very hard to do. Okay, and kind of the key insight that I want to share, because it's very simple, is that this blurring, the operation of blurring is basically the operation of, it gets translated to a pure loss channel in this infinite dimensional picture. So why? Because blurring means that you add some noise and some excitations can get scattered into the environment. So it's modeled by this pure loss channel, kind of this beam splitter that scatters some excitations in the environment. Okay. Right. So there's also another problem that you can solve with the same blurring technique, but I won't discuss that. But it's basically the same problem, but this time you look at the type 1 error probability decay instead of the type 2 error probability decay. This is called the generalized sum of theorem that we also solve in this paper with Mario Berta and Bartosz Regula. And what you get is not the relative entropy of entanglement or its regularized version, but the reverse relative entropy of entanglement, in which you take the minimum over separable states on the first argument. Quite bizarre, right? But the good news there is that you don't need any regularization. You can actually compute this. It's a single letter quantity, not a limit in n. Okay, I want to conclude with a summary. So I hope I convinced you that this GQSL, the generalized quantum science lemma, connects quantum hypothesis testing and quantum resource manipulation in a very fundamental way. It has a long history, and here we have one of the complete proofs out there. And these two main techniques that I introduced are blurring and this bosonic lifting operation. That's kind of a bit mysterious. But there are other open problems that are still not that are more difficult. For example, Höfting error exponents, or the case where you have an almost IID source, and also when you have a composite hypothesis of both arguments. These are all very mysterious so far. And with that, I thank you.
Okay, so any questions? I can start with one. So I'm wondering, so this blurring thing, I mean, I can imagine many ways to do blurring, but you have this particular way of doing blurring. Could you, somehow the symmetry is very important here. Could you say a few words why this particular way of
No, as you say,
blurring,
it's exactly like this. So there are several ways to do this, and they're both all equivalent, and they're kind of essentially all equivalent. You just have to go with, for example, instead of adding, you can add essentially any state. You could be adding the maximum mixed state instead of the full rank free state, but they're all equivalent. You can prove that they're all mathematically equivalent. So it's kind of the essence is there somehow. But yeah, I agree. There are many ways.
this bosonic lifting thing, does it occur anywhere else, like this technique?
No, exactly. So this is why it's very mysterious. There is no good reason why it should be there. So it's just a hack that I came up with because I don't know how to analyze the finite end limit in the quantum case. In the classical case, yes, I can do one shot. I can have one-shot bounds, convergence bounds, everything explicit. But in quantum case, no. So far, no.
Any intuition why embedding into an infinite dimensional space somehow makes it easier?
Yeah, well, because you like for harmonic oscillators, you know all sorts of things, right? You have coherent states, you have the Segal-Bargman transform that's holomorphic function. So you need at some point there are properties of holomorphic functions coming into play. It's just completely very bizarre, I would say. But yeah, somehow in infinite dimension, you know much more because for harmonic oscillators, we have a whole theory of quantum information there. And it's kind of, but I agree, it's kind of really bizarre that you should go all the way there to solve the problem.
So you mentioned this like simultaneous proof of the same theorem. Is it like logically inequivalent, or are they somehow like using?
Oh no, this is the interesting part. They are completely unrelated. So like the techniques are very different. So Hayashi and Yamasaki's one is it's kind of very standard quantum information, and in some ways it's even simpler, I would say. It uses a technique called pinching. It's kind of very standard in quantum information, in hypothesis testing especially. But it kind of, so this is why I think this is very interesting that we have two different proofs that kind of they use very different techniques, and in fact they give you different perks. So with Hayashi and Yamasaki's one, you can drop some of the axioms. For example, you can drop two of the axioms. That's kind of nice. While with mine, yeah, I think you have to keep all of them. Maybe you can drop one, but I'm not sure. What you can do with mine is that you can move, you can state a claim for, you can basically do entanglement testing against, for not only for IID states, so for row tensor n versus separable states, but for almost IID states. So for sources that only approximately output IID states. And this almost IID states, they have a long history in quantum information theory. For example, Renato Renner introduced them long ago because they pop up in cryptography. And somehow, like my proof is it's very natural in that setting. It extends very naturally there. But and Hayashi and Yamasaki's one, not really. And also the other difference is that this blurring technique is used also to prove this Sanov theorem. So in fact, the Sanov theorem was an open problem in another paper by Hayashi. And okay, so he couldn't solve it. So we assume that his technique doesn't work for this one. we kind of tried a bit, but couldn't make it work. So maybe there's a hack also there that we haven't found, but doesn't seem to, at least he couldn't do it. So, but with blurring, it's kind of, in fact, with classical blurring, you can solve this, and it's kind of easy. So yeah, they give you different perks. So it's kind of very different.
Okay. And
So it seems that somehow like relaxing this non-entangling operation to an asymptotically non-entangling operation really has a very significant effect. Like it now makes the process reversible. So do you have some intuition for why, or like does the proof provide some understanding of why that's the case?
So the fact that non-entangling operations don't suffice, exactly non-entangling operations don't suffice, this was actually Bartosz Regula and I proved this a few years ago, 2021, I think. And it's also a hack. We don't really know. We provide one example of state for which the stable entanglement is more cost, but we don't really have any good why it doesn't work. So somehow like you need this small amount of entanglement to be injected in the system to oil the mechanism of entanglement distillation. It's entanglement distillation that gets stuck. Entanglement dilution, no, sorry, it's the other way around. It's entanglement dilution that gets stuck. Entanglement distillation is fine. You can also, so under non-entangling and asymptotically non-entangling, it's the same rate. But entanglement dilution, for some reason, no. So you can lower the cost by injecting this small amount of entanglement. But it's been mysterious. I don't have a good answer.
okay, so let's thank Ludovico again for this remarkable proof. Now we have lunch served at the patio. We're gonna have another Q-Farm seminar talk in a different venue, starting at 1. So for those interested, we can work together over there 10 minutes before 1. And